Welcome to lecture number 17 of the course Computational Hydraulics. We are in module 2 numerical methods, and this is unit 13 finite volume method upwind approach. In our previous lecture we have seen that numerical flux function approximation is important. We cannot use arbitrary approximation of the numerical flux function. If we use averaged value of the flux of two adjacent cells for the interface, we are getting unstable schemes. At the same time, adding some extra term or virtual term in the equation gives stability to the numerical discretization. So, in this particular lecture, we will be concentrating on upwind approach. Learning objective, at the end of this unit, students will be able to discretize the conservation laws using upwind method. We already know this is our conservative form in terms of phi, f phi and s phi. Let us consider the simple approximation of the flux for linear case, where a phi is the linear approximation. Now, cell averaged value can be approximated for this case, where the information is travelling. Let us say this is xe point, this is x axis, this is point xe, this is xe. So, information is travelling at certain speed. So, in this case this line is linear, or this is characteristic line. So, information which is travelling from level n to n plus 1, in this case phi e t plus delta t, that is from phi e minus a delta t. A delta t is the distance travelled in this case. So, essentially we are using the previous time level value for calculation of future time level values directly. In this case, future time level values can be directly expressed in this form, where this phi p or phi p n plus 1 can be written in terms of convex combination of phi w and phi p. Convex combination means in this case our consideration is a greater than 0, that is why it is travelling on the right side. So, this weight functions, if we add these two weight functions, the summation will be equal to 1. So, phi p we have written in terms of phi w and phi p, and phi e n plus 1 we can write it in terms of phi e and phi p, phi e and phi p. Again convex combination for this one. If we simplify this with our approximation thing, we can get these form. In this case, CFL condition for a greater than 0 is a delta t delta x. We have seen this derivation of the CFL condition from stability criteria for our finite difference approximations. A delta t equals to 1, a delta t by delta x equals to 1 or Coulomb number equals to 1. That means the information which is travelling from the nth level and reaching to the n plus 1 level, this is exactly for point E, whatever is there in the point P, that is directly getting transferred to point E. Or in this case, if we have E equals to 1, so obviously this is phi w n, or in this case if this is equal to 1, again this is phi p n. That means if a greater than 0, the information of the previous cell is directly getting transferred to the right word cell in the future time level. In Upwind, time stepping is important. So, in this case, information is travelling from P cell to E cell or E cell to, this part is information is travelling from P cell to E cell. In this case, information is travelling from E cell to E cell. But if we increase this time step, then we can see that information transfer will be there from W cell and P cell. So, time stepping is important. This is controlled by CFL condition or Courant-Frederick-Lewis condition. Upwind method, let us say that we are considering a greater than 0 condition. If I have P cell, W cell, E cell, we have different values. Now, information at the cell interface that is getting transferred to the next cell, and we are getting the average values. So, upwind method can be explained from the wave propagation point of view. At W phase, jump, we can see that WW is the jump from this phi w to phi p, can be conceptualized at a wave moving into P cell at velocity E a in this case, and this wave modifies the value of phi at each point by minus WW, this value, and wave moves a distance a delta t over time step and passes through a delta t by delta x fraction of the cell. So, we can write it like this. In this case, we have a general equation where we have general flux function for E cell and W cell. A greater than 0, we can approximate this numerical flux as A phi p. That means at the interface of the cell P and E, of the cell P and E, information is travelling from P cell to E cell. So, we can say that the approximate value of numerical flux will depend on this cell P, which is upgradient cell, and for W phase, this is W because information is travelling from W to P for W phase. So, if we consider A less than 0, this will be modified because at cell interface E, the information will be travelling from E to P side, and at W phase from P to W side. So, the corresponding values are utilized here. At E phase, the wave propagation, again we can write it like this, and CFL condition, if we do not consider absolute value of A, then this will be just opposite to our original condition. Original condition was A delta t by delta x equals to 0. Sometimes we use combined criteria where A delta t delta x is utilized. This will be always this will be always 1 in this case. In general form, if we write, then this is written as considering both A greater than 0 and A less than 0, A minus E and A plus P. At E cell, if A or information is moving in the positive direction or positive x direction, then we should consider P cell value, or in negative direction E cell value. In this case, if it is for W phase, if it is our negative direction, we should consider P cell value. At W phase, if we have a positive direction thing, then we should consider W cell value. So, this is general format, but what is the interpretation of this? If A greater than 0, A greater than 0 some number, so obviously A plus will be maximum of A or 0, that means this will be A, and minimum of A 0. That means if A is positive here, this quantity will be 0, but this will be A. That means only P will be considered and W will be considered if A greater than 0. But if you have A less than 0, less than 0 means in this case minimum will be considered. So, this will be A, and maximum of negative quantity and 0. So, this will give 0 value. So, in this case we will have E and P terms or first terms. Now, we can write our final form like this. We have just regrouped it with the coefficients A minus and A plus. Now, we can see that from our previous case, we have unstable schemes and stability with with some modification in the equation itself. But in this case we do not require any modification as such, but depending on the nature of the problem or characteristics of the problem, we are defining the interface values, and at the same time we are defining the numerical flux. So, this is this approach is more physically consistent, and this is the basic thing for our upwind approach. This approach is called as first order upwind method. Thank you.